Chapter 7. Experience Compressed. Decline. I started watching cephalopods closely, following them around in the sea around 2008. First the giant cuttlefish, and then octopuses, once I'd learned to see them. They'd been all around me, of course, the whole time. I also started reading about them, and one of the first things I learned came as a shock. Giant cuttlefish, these large and complicated animals, have very short lives, just 1 or 2 years. The same is true of octopuses. 1 or 2 years is a common lifespan. The largest, the giant Pacific octopus, can make it to about 4 years at the outside. I could hardly believe it. I'd assumed that the cuttlefish I'd been interacting with were old, had met humans often and worked out how they behaved, and had seen many seasons pass in their patch of ocean. I'd assumed this partly because they seemed old. They had a worldly look. They also seemed too big to be so young, as they were often 2 or 3 feet long. I realized that year, though, that I'd come across these cuttlefish in the early part of the breeding season, and all the animals I'd been visiting would soon be dead. Indeed, that is how it went. Toward the end of that southern winter, the cuttlefish entered a sudden decline. It was visible over weeks, sometimes over days, when I was able to follow a single individual. They spontaneously began to fall apart. Soon some were missing arms and clumps of flesh. They began to lose their magical skin. At first I thought some of them were producing white patches as part of a display, but a closer look showed that the outer layer of skin, the living video screen, was instead falling off, leaving plain white flesh behind. Their eyes went cloudy. As this process reaches its end, the cuttlefish is unable to control its height in the water. Once the decline starts, it occurs very quickly. Their health seems to drop off a cliff. Once I knew this stage was coming, interacting with these animals, especially the friendly ones, became poignant. Their time was so short. This discovery also made the puzzle of their large brains even more acute. What's the point of building a large nervous system if your life is over in a year or 2? The machinery of intelligence is expensive, both to build and to run. The usefulness of learning, which large brains make possible, seems dependent on lifespan. What is the point of investing in a process of learning about the world if there is almost no time to put that information to use? Cephalopods are evolution's only experiment in big brains outside of the vertebrates. Most mammals, birds and fish live a lot longer than cephalopods. More accurately, the mammals and birds can live longer if they don't get eaten or encounter some other mishap. This is especially true of larger species like dogs and chimps, but there are monkeys the size of a mouse that can live for 15 years, and hummingbirds that can live for over 10. Many cephalopods seem both too big and too smart to race through their lives in the way they do. What is all the brain power doing if an octopus is dead less than 2 years after hatching from the egg? Could there be something about the sea which imposes a short life? I quickly found out that is not the answer. A strange-looking rock-dwelling fish that inhabits the same patch of sea as my cephalopods is from a group that includes fish who live to 200 years of age. 200. This seemed extraordinarily unfair. A dull-looking fish lives for centuries, while the cuttlefish, in their splendor, and the octopuses, in their curious intelligence, are dead before they are 2. The cephalopod situation is reminiscent of Ridley Scott's movie Blade Runner, in which a class of artificial but human-like replicants are programmed to die after only 4 years. In the book by Philip K. Dick on which the film was based, Do Androids Dream of Electric Sheep?, their early deaths are due to breakdown. Blade Runner's replicants, unlike cephalopods, know their fate. Another possibility was that something about the mollusk body plan or something about cephalopods makes a short life inevitable. I sometimes hear people say this, but it can't be the answer. Nautiluses, the elegant but psychologically unimpressive cephalopods who steer their shells like submarines around the Pacific, can live for more than 20 years. That is, several drawn-out decades of life for what biologists unflatteringly have called a smell and grope scavenger. These animals are relatives of octopuses and cuttlefish, and they're not rushing through their lives at all. All this gave rise to a very different sense of what an octopus's or cuttlefish's life is like. Rich in experience, but incredibly compressed. It also gave rise to more puzzlement about the brains that make that experience possible. Life and death. Why don't cephalopods live for a longer time? Why don't we all live for a longer time? On mountainsides in California and Nevada, there are pine trees that were alive when Julius Caesar was wandering around Rome. Why do some organisms live for dozens, hundreds, or thousands of years, while others, in the natural course of events, do not see even a single year pass? Death from accident or infectious disease is no puzzle. The puzzle is death from old age. Why, after living for a time, do we fall apart? This question is always lurking as the birthdays pass, but the short lives of the cephalopods make it vivid. Why do we age? We tend to think about this intuitively as a matter of bodies wearing out. Some might say we must wear out eventually, just as an automobile does. But the automobile analogy is not a good one. An automobile's original parts will indeed wear out, but an adult human is not operating with his or her original parts. We are made of cells that are continually taking in nutrients and dividing, replacing old parts with new ones. Even a cell that stays alive for a long time is continually turning over its material. Most of it, anyway. If you keep replacing the parts of an automobile with new ones, there's no reason why it should ever stop running. Here is another way to see the puzzle. Our bodies are collections of cells. These cells are stuck together and work in a coordinated way, but they are just cells. Most of the cells that make us up are continually dividing, creating two from one. Suppose that for some reason these dividing cells were bound to get old, even though the cells actually present now have not been around very long. That is, suppose that even newly arrived cells show the age of their lineage, and this age is responsible for a body's decay. But if that is how things work, why do bacteria and other single-celled organisms still exist? The individual bacteria that are around now are the products of cell divisions that took place in the recent past, but their cell lineages are billions of years old. Imagine taking a lot of bacteria of a particular kind, the familiar E. coli perhaps, and putting them together in a clump. When those cells divide, their offspring cells stay in the same clump, so the clump persists as cells come and go. If conditions were favorable, that clump might persist for millions of years. The clump would be a kind of body, a big collection of cells. There is no reason for it to wear out or break down just because it is old. Again, the parts present now are not old, they're brand new cells. If that clump of cells can live forever, replacing and replenishing, then why not the clumps that are our bodies? You might now say it is the arrangement of our cells that makes us different from the bacteria. We are not just a clump. This arrangement can break down even if the cells are always new. But why can't new cells remake the right arrangements? Cells can generate the right arrangement when a person is conceived, born, and develops from a baby to an adult. Why can't the arrangement needed to keep you alive be constantly regenerated by the newly arriving cells? Explanations in terms of parts wearing out are not enough to resolve the problem. Even if there is a version of this idea that does make sense, it fits poorly with many observations of lifespan in animals. If wearing out is the issue, then animals which have a faster metabolic rate, which burn through more energy, should age faster. This relationship has some predictive power, but it falls down in a fair number of cases. Marsupials such as kangaroos have lower metabolic rates than placental mammals like us, but they age faster. Bats have furiously active metabolisms, but they age slowly. At the level of cells, there is the possibility of indefinite renewal. But something about the kinds of objects we are, the kinds of collections of cells we are, gives us and other animals a relation to aging that is different from that of other living things. This way of looking at the issue takes us back many chapters to the evolution of animals themselves. In animals, birth and death have come to exist as boundaries that mark out an individual life, even though cells are continually coming and going, and even though the cell's lineages extend before us and after us. So, again, we face the problem. Why do hummingbirds live till they are 10, rockfish till they are 200, bristlecone pines till they are thousands of years old, and octopuses until they are 2? A swarm of motorcycles. These puzzles have been largely resolved through some elegant pieces of evolutionary reasoning. If we're thinking in evolutionary terms, it's natural to wonder if there is some hidden benefit from aging itself. Because the onset of aging in our lives can seem so programmed, this is a tempting idea. Perhaps old individuals die off because this benefits the species as a whole, by saving resources for the young and vigorous. But this idea is question-begging as an explanation of aging. It assumes that the young are more vigorous. So far in the story, there's no reason why they should be. In addition, a situation of this kind is not likely to be stable. Suppose we had a population in which the old do graciously pass the baton at some appropriate time, but an individual appeared who did not sacrifice himself in this way and just kept going. This one seems likely to have the chance to have a few extra offspring. If his refusal to sacrifice was also passed on in reproduction, it would spread, and the practice of sacrifice would be undermined. So even if aging did benefit the species as a whole, that would not be enough to keep it around. This argument's not the end of the line for a hidden benefit view, but the modern evolutionary theory of aging takes a different approach. The first step was made in the 1940s by a British immunologist, Peter Medawar, in a brief verbal argument. A decade later, the American evolutionary biologist George Williams added a second step. A decade on again, in the 1960s, William Hamilton, probably the genius of late 20th century evolutionary biology, put the new picture into rigorous mathematical form. Though the theory has been made precise in this way, the crucial ideas are satisfyingly simple. Start with an imaginary case. Assume there is a species of animal with no natural decay over time. These animals show no senescence, to use the word preferred by biologists. The animals start reproducing early in their life, and reproduction continues until the animal dies from some external cause, being eaten, famine, lightning strike. The risk of death from these events is assumed to be constant. In any given year, there is a, say, 5% chance of dying. This rate does not increase or decrease as you get older, but there is some number of years by which time some accident or other has almost certainly caught you. A newborn has less than a 1% chance of still being around at 90 years in this scenario, for example. But if that individual does make it to 90, it will very probably make it to age 91. Next, we need to look at biological mutations. Mutations are accidental changes to the structure of our genes. This is the raw material of evolution. Very rarely a mutation occurs which makes organisms better able to survive and reproduce. But the vast majority of mutations are harmful or have no effect at all. Evolution produces what is called a mutation selection balance with respect to many genes. This works as follows. Mutated forms of a gene are constantly entering the population as a result of molecular accidents. Individuals with the mutated form are less likely to reproduce, so the bad mutations are eventually lost from the population. But even if every bad mutation is lost, that process takes time, and new mutations also keep coming in. So we expect a population to always contain some harmful mutated forms of each gene. A mutation selection balance is a situation where bad mutations of a gene are being weeded out just as quickly as they are being introduced. Mutations often tend to affect particular stages in life. Some act earlier, others act later. Suppose a harmful mutation arises in our imaginary population which affects its carriers only when they've been around for many years. The individuals carrying this mutation do fine for a while. They reproduce and pass it on. Most of the individuals carrying the mutation are never affected by it because some other cause of death gets them before the mutation has any effect. Only someone who lives for an unusually long time will encounter its bad effects. Because we're assuming that individuals can reproduce through all their long lives, there is some tendency for natural selection to act against this late-acting mutation. Among individuals who live for a very long time, those without the mutation are likely to have more offspring than those who have it. But hardly anyone lives long enough for this fact to make a difference, so the selection pressure against a late-acting harmful mutation is very slight. When molecular accidents put mutations into the population, as described previously, the late-acting mutations will be cleaned out less efficiently than early-acting ones. As a result, the gene pool of the population will come to contain a lot of mutations that have harmful effects on long-lived individuals. These mutations will each become more common or be lost mostly through sheer chance, and that makes it likely that some will become common. Everyone will carry some of these mutations. Then if some lucky individual evades its predators and other natural dangers and lives for an unusually long time, it will eventually find things starting to go wrong in its body as the effects of these mutations kick in. It will appear to have been programmed to decline, because the effects of those lurking mutations will appear on a schedule. The population has begun to evolve aging. The second main element in the theory was introduced by George Williams, an American biologist, in 1957. This is not a rival to the first idea. They are compatible. Williams's main point can be introduced by asking a simple question about saving for retirement. Is it worth saving enough money so that you will live in luxury when you're 120? Perhaps it is if you have unlimited money coming in. Maybe you will live that long. But if you don't have unlimited money coming in, then all the money you save for a long retirement is money you can't do something else with now. Rather than saving the extra amount needed, it might make more sense to spend it, given that you're not likely to make it to 120 anyway. The same principle applies to mutations. A lot of mutations have more than one effect, and in some cases a mutation might have one effect that is visible early in life and another effect that is visible later. If both effects are bad, it's easy to see what will happen. The mutation should be weeded out because of the bad effect it has early in life. It's also easy to see what will happen if both effects are good. But what if a mutation has a good effect now and a bad effect later? If later is far enough away that you will probably not make it to that stage anyway due to ordinary day-to-day risks, then the bad effect is unimportant. What matters is the good effect now. So mutations with good effects early in life and bad effects late in life will accumulate. Natural selection will favor them. Once many of these have arisen in the population and all or nearly all individuals carry some of them, a decay late in life will come to seem pre-programmed. Decay will appear in each individual as if on a schedule, though each individual will show the effects a bit differently. This happens not because of some hidden evolutionary benefit of the breakdown itself, but because the breakdown is the cost paid for earlier gains. The Medawar effect and the Williams effect work together. Once each process gets started, it reinforces itself and also magnifies the other. There is positive feedback, leading to more and more senescence. Once some mutations get established that lead to age-related decay, they make it even less likely that individuals will live past the age at which those mutations act. This means there's even less selection against mutations which have bad effects only at that advanced age. Once the wheel starts turning, it turns more and more quickly. The picture I've been developing here is one full of pressures pushing downward on lifespan. But what about the 1,000-year-old pine trees in California? They show no signs of falling apart. Trees are special, however, in two ways. First, they do not fit an assumption I made at an early stage of the argument earlier. I said that differences between how successful individuals are at reproducing late in life are not evolutionarily important because almost no individuals make it to that stage. But things are different if the few individuals who do succeed in reproducing when they are very old can have very large numbers of offspring. This is not true of us, but it is true of trees. Every branch on a tree is a site at which reproduction can take place. So a very old tree with its many branches can be much more fertile than a young tree. This enables trees to avoid some of the consequences of Medawar and Williams's arguments. Second, a tree is a different kind of living thing from an animal, and to some extent the Medawar-Williams arguments do not even apply to it. The best way to approach this point is to first consider those organisms that can be seen when you look closely to actually be colonies. Some sea anemones, for example, form tight-knit colonies consisting of many small polyps, which have a good degree of independence, especially in reproduction. One polyp can bud off another, and each polyp can make its own sex cells. These colonies can live indefinitely in principle, just as a human society might, with individual humans coming and going, but the society itself persisting. Colonies and societies are not subject to the Medawar and Williams arguments because they do not reproduce in the right way. The members of the colony or society, such as humans, can show senescence instead. An ordinary tree, like a pine or an oak, is not a colony, but it is not a single organism in quite the way a human being is either. In some ways, it is in between those two cases. A tree grows by the multiplication of small units, branching stems that can each reproduce on their own, and if cut and transplanted can give rise to another tree. Anything that grows and develops through the multiplication of units that can reproduce in this way is exempt from the Medawar-Williams arguments. I've introduced the two main ideas behind the evolutionary theory of aging. In the 1960s, the theory was made rigorous and precise when the English evolutionary theorist William Hamilton turned his huge mind toward the problem. Hamilton recast the central ideas in mathematical form. Though this work tells us a good deal about why human lives take the course they do, Hamilton was a biologist whose great love was insects and their relatives, especially insects which make both our lives and an octopus's life seem rather humdrum. Hamilton found mites in which the females hang suspended in the air with their swollen bodies packed with newly hatched young, and the males in the brood search out and copulate with their sisters there inside the mother. He found tiny beetles in which the males produce and manhandle sperm cells longer than their whole bodies. Hamilton died in 2000 after catching malaria on a trip to Africa to investigate the origins of HIV. About a decade before his death, he wrote about how he would like his own burial to go. He wanted his body carried to the forests of Brazil and laid out to be eaten from the inside by an enormous winged Coprophaneus beetle, using his body to nurture its young, who would emerge from him and fly off. No worm for me, nor sordid fly. I will buzz in the dusk like a huge bumblebee. I will be many, buzz even as a swarm of motorbikes, be borne body by flying body out into the Brazilian wilderness beneath the stars, lofted under those beautiful and unfused elytra wing covers, which we will all hold over our backs. So finally I too will shine like a violet ground beetle under a stone. Long and short lives. The evolutionary theory of aging gives us an explanation for the basic facts of age-related decay. It explains why breakdown starts to appear in old individuals as if on a schedule. More can be added to this outline to enable it to describe particular cases. In my thought experiment earlier, I assumed that reproduction takes place all through an organism's life. In many animals, including cephalopods, this is not even close to how things work. Biologists distinguish between semelparous and iteroparous organisms. Semelparous organisms reproduce once or in a single short season. This is also called Big Bang reproduction. Iteroparous organisms like ourselves reproduce many times over a more extended period. Female octopuses, in general, are an extreme case of semelparity. They die after a single pregnancy. A female octopus might mate with many males, but when it is time to lay eggs, she settles permanently into a den. There the female will lay her eggs and fan and tend them as they develop. This one clutch can contain many thousands of eggs. The brooding might take a month or several months, depending on the species and the conditions. Things are slower in cold water. When the eggs hatch, the larvae drift off into the water. Soon afterward, the female dies. I'm generalizing here. There's at least one exception among the octopuses, a rare species found in Panama by the same team that studied the squid signals, discussed in Chapter 5, Martin Moynihan and Arcadio Rodoniche. In their species, the females can reproduce over a longer period. No one knows why they're an exception. Cuttlefish are a little different, but they still fall within the Big Bang category. They're active only in a single breeding season, but both sexes can engage in many matings, and the females can produce many batches of eggs in that season. The females do not tend and protect the eggs as octopuses do, but glue them to rocks of a suitable kind and leave them, moving off to mate and lay again. Then, as I described at the start of this chapter, they rapidly fall apart. Why should an organism devote all its resources to one brood or one breeding season? Much depends again on the risk of death by predation and other external causes, especially on how this risk changes over an animal's lifetime. Suppose in some animal the juvenile stage is risky, but once you get to be an adult you can expect to live for a while without being eaten. Then it makes sense for adults to reproduce more than once. That applies to fish and many mammals. If, on the other hand, the adult life stage is very risky, it might make more sense to go for broke as soon as you get to a stage where you can breed. Seasons also play a role. There might be a good season for laying eggs or for hatching. That will determine a timetable within each year. Perhaps it makes sense to mate in spring or in winter. Then the question becomes, during how many years should you try to reproduce? Initially, it might seem obvious that there's no harm in leaving it open, at least that you will be around for another couple of years. You might make it through. Why fall apart in the meantime? But here the Williams argument returns, along with the need to think about these evolutionary questions by considering vast numbers of individuals and many generations. In the abstract, you would like to live and mate forever, at least from an evolutionary point of view, but who will leave more descendants? An organism which spends everything on one mating season, or a rival which spends less now in the hope of reproducing again later? If you spend less now to save something for later, that will do you no good if animals of your kind have little chance of making it to the next breeding season. In that case, it's better to put everything into one mating season, embracing all the options which give you an advantage now, even at the cost of breakdown once the season is done. Evolution can give a species a vast lifespan or a tiny one. Within animals, the 200-year-old rockfish and the cuttlefish are extreme cases, and humans are intermediates. We and the rockfish both mature fairly slowly and reproduce over a number of years. But the rockfish goes on for longer. It is a spiny, venomous creature that no one tries to eat. The cuttlefish, in contrast, races to become large and fertile, mates in one season, and then falls to pieces. The lifespans of different animals are set by their risks of death from external causes, by how quickly they can reach reproductive age, and other features of their lifestyle and environment. That is why we can live for about a century. A nondescript fish can live for twice as long, A pine tree's life can run from John the Baptist's to your own, and a giant cuttlefish, with its wild colours and friendly curiosity, arrives and is gone in a couple of summers. In the light of all this, I think it's becoming clearer how cephalopods came to have their peculiar combination of features. Early cephalopods had protective external shells which they dragged along as they prowled the oceans. Then the shells were abandoned. This had several interlocking effects. First, it gave cephalopod bodies their outlandish, unbounded possibilities. The extreme case is the octopus, with almost no hard parts at all, and neurons spread through the body instead of bones. Back in Chapter 3, I suggested that this open-endedness, this sea of behavioral possibility, was crucial to the evolution of their complex nervous systems. It's not that the loss of a shell alone created the evolutionary pressure leading to those nervous systems. Rather, a feedback system was established. The possibilities inherent in this body create an opportunity for the evolution of finer behavioral control. And once you have a larger nervous system, this makes it worthwhile to further expand the body's possibilities, collecting all those sensors on the arms, creating the machinery of color change, and a skin that can see. The loss of the shell also had another effect. It made the animals much more vulnerable to predators, especially fast-moving fish with bones and teeth and good vision. That put a premium on the evolution of wiles and camouflage. But there is only so much those tricks will achieve. Only so many times they will save the animal. An octopus can't expect to live a long time, especially as they must be active as predators themselves. They can't just hide in a hole and wait for food to come to them. They have to be out and about. And once in the open, they are vulnerable. This vulnerability makes them ideal candidates for the Medawar and Williams effects to compress their natural lifespan. A cephalopod's lifespan has been tuned by the continual risk of not making it to the next day. As a result, they have ended up with their unusual combination, a very large nervous system and a very short life. They have the large nervous system because of what those unbounded bodies make possible and the need to hunt while being hunted. Their lives are short because their vulnerability tunes their lifespan. The initially paradoxical combination makes sense. This picture is supported by the recent discovery of an exception to the usual cephalopod pattern. An exception that illuminates the rule. Most of what I've said about octopuses has been based on species that live in fairly shallow water among reefs and shorelines. Much less is known about species that live in the true depths of the sea. A marine research unit at Monterey Bay, California, MBARI, explores deep-sea environments with remote-controlled submarines that carry video cameras. In 2007, they were inspecting a rocky outcrop nearly a mile underwater, off the coast of central California. They saw a deep-sea octopus, Granelidone boreopacifica, moving around. Returning a month or so later, they found the same octopus guarding a clutch of eggs. They kept returning to the site to watch the progress of this clutch of eggs and always found the octopus there. In the end, they watched this one octopus for 4.5 years. This octopus brooded her eggs for longer than any other known octopus is thought to live in total, and the 53 months it spent there is the longest egg-brooding period reported for any animal species. For example, no fish is known to guard its eggs for more than 4 or 5 months. It's not known how long this species of octopus can live, but as the report by Bruce Robeson and his colleagues notes, if it spends the same fraction of its life brooding as other octopuses do, it might live for something like 16 years. This is strong evidence against any suggestion that octopus bodies pose some physiological barrier to a long life. But why does this octopus live for so long when other species do not? The paper by Robeson and his colleagues discusses how water temperature can make biological processes go more slowly. Deep waters are usually very cold, and I can't help being reminded of the fact that the one time I went scuba diving near Monterey, I was colder than I've been in my life. Much of life runs in slow motion in cold water. Robeson and his co-authors think this is part of the reason the mother can stay alive for so long, apparently without feeding. The paper also notes that the long brooding enables the young to hatch in a large and advanced state. Robeson thinks that in this environment the egg's lengthy development gives an octopus a competitive advantage. I'd also suggest that the Medawar-Williams theory has a role to play, though. This theory predicts that predation risks should be much less severe for this species than they are for shallower water octopuses, as the risk of predation affects an animal's natural lifespan. And here, there is a strong clue. The MBARI images show an octopus sitting out in the open with her eggs for years on end. She did not find herself a den. Shallow water octopuses do not, as far as I know, ever brood eggs out in the open like this. They would be sitting ducks for any predator that came along. In the deep sea, though, fish are much rarer than they are in the shallows. The fact that the Monterey octopus successfully brooded eggs in the open suggests that this species had less to fear from predation than other octopuses do. As a result, evolution has tuned its lifespan differently. Putting these things together, we can see how many of the features of cephalopods, especially those features so pronounced in the octopus, might have stemmed from the abandoning of the shell all those years ago. This abandonment set them on a path of mobility, dexterity, and nervous complexity, and it also led to a live-fast, die-young lifestyle, an existence always exposed to the sharp-toothed predators around them. Ghosts. I was diving in Sydney one day, a little away from my usual sights. Suddenly things went dark, and it was a moment before I realized I'd swum into a massive cloud of ink. This was in an area scattered with boulders, gathered close with deep crevices between them. The inked area was the size of a large room. Everything was gunpowder grey with thick black stringy shapes suspended here and there. There was too much ink to see what was going on, especially down in the crevices, and the ink hung there for a long time. The next day I had a look in the same area. There was no ink, but I began to see dozens of cuttlefish eggs strewn across the sand at the bottom of some of the crevices. There was also a giant cuttlefish nearby. It was in awful condition. Its body was mostly white, and there was much damage on the arms. It watched me, hovering. Looking closer, I found 3 more, all quite large, clustered under a Stonehenge-like structure, with a natural rock roof that rose several meters off the bottom of the sea. One cuttlefish was clearly male, and the others seemed to be female, but it was hard to tell. They were all in various stages of decay. The worst off had lost much of their skin, leaving bare pearl-white bodies underneath, with fanning and criss-crossed cracks, like broken glass in the skin that remained. Those who had more skin were pale grey. Some had eyes in very bad shape. A 5th cuttlefish, with some strong yellow left in her skin, swam in. But 5 of her arms were largely gone, and there were dark wounds in the flesh that remained. She swam off. The 4 cuttlefish drifted about close to one another, wafting in tiny currents among the rocks. The eggs strewn on the seafloor were puzzling. Giant cuttlefish usually attach eggs to the roof of a ledge of some kind, where they hang down like tulip bulbs. I couldn't tell if these eggs had come adrift from where they were supposed to be, or had been laid where they were now. The ink I'd seen the previous day suggested that something might have gone wrong, but I had no idea what. The cuttlefish paid no attention to the eggs. They seemed to be just waiting. They also appeared to watch me, but with very little display, and I was not sure that all of them could still see me at all. Pale and quiet, they looked like cephalopod ghosts. For some days there were cuttlefish there. There seemed to be arrivals and departures. The eggs remained down at the bottom of a crevice, lying in dim light with silt around. Finally I was there when one of the female cuttlefish reached the end. She was floating just outside the crevice when I arrived. A lot of her skin had been lost, with patches of orange-brown remaining. 2 of her arms had gone completely, and one of her feeding tentacles hung motionless. She was still swimming, with her fins moving gently. As I watched, I realized that we were both climbing a little in the water column, leaving the rocky crevice. Soon 2 fish took an interest in her. A pink fish began to circle, but did not attack. A large leather jacket was more of a problem. It came in, looked and circled, and then began a series of attacks trying to bite pieces out of the front of the cuttlefish, even though the victim was several times larger than the attacker. I tried to keep the fish away, but it would not retreat far and resumed its assaults whenever it could. In response to the first attacks, the cuttlefish just flinched and waved her arms, with no effect at all. The fish kept coming. I realized that my attempts to defend the cuttlefish seemed to cause more panic in the cuttlefish than the fish's attacks. I was too big to be that close. The leather jacket came in again and bit harder, and this time the cuttlefish inked at it. The fish was not much deterred, and approached again. Now the cuttlefish inked more profusely and also began to spiral slowly. We continued to rise passively in the water. With the slow spiral and with grey-black ink pouring out of her funnel, the cuttlefish looked like a lumbering airplane on fire, an airplane which rose rather than fell to earth. Either because of the ink or the height we had now reached in the water, the fish abandoned its attacks. But this was all the cuttlefish could do. As she kept rising, the spiral stopped. She came up through the last metre of water and was suddenly floating on the surface, completely still. The surface of the water was a mess of small waves, which now sloshed the cuttlefish back and forth. I left her there. The cuttlefish's death was a transition from swimming deep in her quiet world through a slow spiralling ascent to drifting on the noisy surface of ours.